So last time we started section 3.5, we're looking at division of whole numbers. And we had talked about the different models, and I think that we're on our properties. Does that sound right? Okay. So we're going to take a look at the properties that we had seen for multiplication. And let's get over here. Discuss which of them hold for division. All right, closure. Closure means taking, this is for whole numbers, means taking two whole numbers and operating on them with whatever operation, in this case division, and asking ourselves, do I get another whole number? So if I divide a whole number by a whole number, will I always get a whole number? No. Can you give me an example of why not? These are called counterexamples, remember? So 3 divided by 2, which is not an element of the whole numbers, right? Nope, it's not. How about the commutative property? Commutative property has to do with reversing orders. Will reversing orders of division work? No. I need an example. So let's chart with something that actually at least works. How about 6 divided by 2? Is that okay, Ethan? Okay. 6 divided by 2 is a whole number, right? So at least that part's good. But what happens if I try to do 2 divided by 6 the other direction? It's not the same, right? So there's no closure. There's no commutative property. Associative is a little harder to work with, so let's actually just create one side and then switch it and see if it works. At least gives us a good idea of where to start. So if we take, how about I do 8 divided by 2 and then divide that by 2 again. Let's do that. So what would 8 divided by 2 be? 4 divided by 2 would be 2. So if I do all of this in order, I get a number 2. So let's try and see what happens. This is a question mark kind of thing right now. If I do it in the other order. So if I do 8 divided by and 2 divided by 2. So now I'm starting with the parentheses here. What's 2 divided by 2? 1. And what's 8 divided by 1? 8. So doesn't work, right? This one won't work either. Remember, all you have to do is have one example of it not working to say it doesn't hold. So counterexamples are a lot easier to find. I shouldn't say it that way. But they're a lot easier to justify than proving something always does work, at least. How about the identity property? So what was our identity element for the multiplication? It was the number 1. The number 1 is the number we can multiply by, and it doesn't change a value. Will that work for division? Well, let's check. It would be the number 1, right? That's sort of the likely candidate. If I did 5 divided by 1, what do I get? 5. But there's a problem. Do you remember what it is? You can't do it the other way around. What happens when I do 1 divided by 5? Well, in particular, it's not 5, right? It's not even a whole number, but it's not 5. Even if it were a whole number, it's not the number 5. So this one's a no. No identity. If we could call it that, we would almost say it has sort of like a half identity, right? It's not a thing, so don't go quoting me on that. That's not really a thing. But it sort of feels like it halfway works, right? But it doesn't work, actually, going both directions. How about division by 0? We had multiplication by 0, right? Multiply by 0, you get 0. That was cool. But what happens if we try to do division?
I think it depends.
Say that again, Rayleigh.
It depends, because there's you can do 0 divided by 0, but you can do a number divided by 0.
Okay, because if you try to do it the other way around, what happens, Ethan? You get an error. Okay, so 0 divided by 2 would work, and that'd be fine. But if we tried it to the other way around, that should say 0. It doesn't equal 0. In fact, it equals something that we call undefined. Your calculator could say a variety of things. It could just say error. It might actually say undefined. Division by 0 is not a defined operation. And I'd actually like to show you what we mean by that based on what we talked about as being the definition of division. So our definition of division said the following. A divided by B is equal to C. I'm going to put IFF. IFF means if and only if. This only works when A is equal to B times C. Okay, that's the definition that we did from division at the very beginning of 3.5. But think about what happens if there's a division by 0 in it. So imagine this b is 0. If I really wanted to say that I could do a divided by 0 and it equals something, I would have to say that a is equal to 0 times c. But what is 0 times anything? 0, which would mean that the a itself would have had to be 0 to start with, right? Well, that doesn't seem to quite work, does it? I should have been able to do it for any a, and now I've forced myself that a had to be 0 to make any of that work. That's why it's not defined. It's not within the definition, hence defined. Okay, that's why we use that phrase. So division by 0 is a no. Distributive property, again, is another one that is helpful if we just try something to see if it works. So we're going to try one. I'm going to write one down that I have. It's kind of like with associative, we have to be a little bit careful about what we pick. Let's say that we have 20 plus 10 divided by 5. So this should, if it works, equal 20 divided by 5 plus 10 divided by 5. That's what it would look like if I could distribute division. So let's just see if it works. What's 20 plus 10? 30. What's 30 divided by 5? 6. So if I do this, I get a 6 on the left. What's 20 divided by 5? 4. And what's 10 divided by 5? 2. And success, right? It worked. It equals 6. But there's a problem. Do you know what the problem is?
You can't, like, switch them.
There's an order switching problem, just like with the associative stuff and just like with our identity and our 0 property. I can't do it in the other order. So it sort of half works. So let me move this up here so I can show you the half that doesn't work. What if you had 20 divided by 10 plus 5? Right? The division's in the other place, right? Because that's how our multiplication property with distribution worked, is that the number had to be either before it or after it, and both work. So this question then would become, does this equal 20 divided by 5? I'm sorry, 10 is first. 10 and 20 divided by 5. So let's check. What's 10 plus 5? 15. 20 divided by 15? It's not a whole number, right? So it's something, but it's not a whole number. It's 1.5, I believe. Is that right? No, 20 divided by 15. Let me just write it that way for a second. It's 1 point something. 0.25 maybe? I don't know. What's 20 divided by 10? 2. And 20 divided by 5? 4. That's definitely not 20 divided by 15, correct? These are not equal. So again, it sort of half works. That's not good enough. So when we did addition, we had lots of properties. Not a ton, but I mean, we had several, like 4 or 5 of them, something like that, right? And we got to subtraction and we had nothing. And then we get to multiplication and we had more even than we had in addition. And then we get to division and we have nothing. There's no properties that hold. Okay, so what I'd like to do next then is to show you algorithms. We do not have near as many algorithms for division as we've had for the other ones, okay? So there's 2 division algorithms I'm going to show you. One of them you're familiar with, and the other one is an extension of something we've already talked about. And then we're going to do some word problems where we combine operations, like addition with division, or multiplication with subtraction, or something like that going on as we finish up this section. And then there's some computational estimations and stuff like that. Okay, so the division algorithm first that you're familiar with is called the standard algorithm. And it works like this. So you have the number 623, and you're dividing by the number 5. And knowing and being able to work with the division algorithm, the one that you've grown up knowing, truly hinges on you knowing your multiplication facts, right? Unless you're using a calculator, it hinges on that. You really cannot do division very well if you do not know your multiplication facts. So part of me, as a math teacher, says, well, you should know your multiplication facts. I mean, I actually truly believe that you should. I think that's a very good thing. My children in my house don't necessarily agree with me. They're very frustrated, and when I point out the fact that they still don't quite know them and it's now causing them problems for something else, they get irritated with that, right? They don't like that because that's how math really is there's a cumulative effect to a lot of it. That said, there are students who have learning disabilities, and multiplication facts might be something they've got a problem, like an actual reason why they didn't learn them the way that maybe other students did. So our second method that we look at is going to hinge on not necessarily having those memorized. There's always a give and a take. Not having them memorized means it's going to be more tedious to do it. Just warning you, okay? So when we do multiplication or division with our multiplication facts in our standard algorithm, we look at this and we say, one at a time, right? Here's my number 6. How many 5s are in the number 6? There's 1. And we put the number 1 on top of the 6, and we say 1 times 5 is 5. And we put the 5 underneath, and we subtract, and we say 6 minus 5 is 1. And then we bring down the number next to it. It's a 2. So now I've got the number 12. And we ask ourselves something like this. How many 5s are there in 12? There's 2. And so we put the number 2 above it. Okay, but like you have to know the multiplication facts of 5s to do that. So 2 above it. So 2 times 5 is 10. And we subtract. 12 minus 10 is 2. And then we bring down our last, because it's a 3-digit number, our last number 3. How many 5s are in 23? 4. 4 times 5 is 20, and we subtract. And for the level that we're doing right now, we stop, and we do something at the end where we write R3, right? There's a remainder of 3 left over. And then as you move forward further in mathematics, right, you hit about 6th grade or so, you're starting to work with decimals and things like that, and you do the division a little bit differently, or maybe fractions. You write this remainder, the number 3 over the number 5 you were dividing by, those kinds of things. But for the purposes of like the 3rd to 4th grade, this is where we stop. And we say that our answer right here is 124, remainder 3. Okay, but you have to know your multiplication facts to do that. So what are the workarounds for that? Well, I've actually seen one workaround used where students have an accommodation where they actually have the multiplication table on their desk. Or with their material as they're taking tests or quizzes or something like that, or working their homework. So that's one accommodation factor. Aside from just like a note sheet kind of thing, the second algorithm here has the ability to not need to know your multiplication facts. And you might be thinking like, well, how could you possibly do that? Well, you're about to find out. Okay, so this is called repeated addition. Or they call it, what else do they call it? Partial quotients. This book used to use the phrase repeated addition, so you may see that in phrases. But this one is called, or repeated subtraction, repeated subtraction is what I meant to say. Partial quotients. Here's the way it works. Okay, so you're going to write down the number 623, and you can even write it underneath the division sign if you want to, whatever, it doesn't really matter. You won't need the division part of it on the outside. But what you're going to do is you're going to subtract the number 5 in whatever place value you can with zeros following it, like this. So 500 is smaller than 623, so I can subtract 500. But what is 500? Well, it's 100 times 5. Sorry, I got a dot there. Where'd that dot come from? There we go. So I'm going to sort of note to the side. It doesn't matter which side you're noting it on or whatever. This is 100 times 5. And particularly important part is the 100 part, not the times 5. The 5 shows up in the hundreds place. This is 500, and then we subtract. Whoops. All right, so what's 623 minus 500? I've got 123. And I ask myself, can I subtract 500 again? And the answer is no. So now I move one place value down. Instead of subtracting 500, I'll subtract 50. Well, what 50 is it's 10 times 5. Okay, so I'm not going to try and belabor the subtraction point because that's another section we've already talked about. We're just going to move through it. But 123 minus 50 would be what? It'd be 73. In whatever way of subtracting we were doing, it's 73. And I asked myself, can I subtract 50 again? Yes, the answer is yes, so I do it again. So this is another 10 times 5. Again, feel free to just write the 10 down if you wish. And I subtract this when I get 23. Can I subtract 50 again? No. Now I'm kind of out of space, so I'm going to start a new column, but you could continue on down if you have the space to do so. So now I've got the number 23, and I can't subtract 50 again, so now I simply subtract 5s until I run out of space. Not space literally, but like space within the number I'm subtracting. So 23 minus 5, well, this is 1 times 5. So this is a 1. So you really have to minus 5 on all of these. You cannot at this point decide all of a sudden now you know your multiplication tables and you're going to do 4 times 5 and subtract 20. That's defeating the point. Y'all with me on that? Okay, so at this point you cannot shortcut the system. We're still subtracting 5s until we run out of space. So this one's 18, and we'll subtract 5 again for 13, and again for 8, and one last time for 3. And over here, every time I've done 1 times 5. So everything I've highlighted in purple, I've done so with purpose. That's the answer. I have 100, 10, 20. That's 120. 1, 2, 3, 4. 124. Remainder, 3. Because there's a remainder here at the end of 3. Okay? There's a price to pay for not knowing them. That's just it. There's a price to pay. And this is what I tell my daughter every time, the one that's the newest in the U.S., right, is that whenever she can't do multiplication by 8s, that's the one. Anything with 8s, just every time it's a guess. And I was like, here's the deal. You have choices. At this point, you have choices. You can start to memorize them and really learn them, or every single time you can figure out 8 plus 8 plus 8 plus 8 plus 8, however many of you need to, and then figure out what it is. There's a price to pay for not memorizing them. Okay, in her situation, it's not a learning disability. I don't mean to be disrespectful for the children who are. But in her situation, it's a lack of really wanting to memorize, right? There's a price to pay. She can choose to not memorize them, but then she's going to be doing that every time she has to work with 8s. Okay, so this is our second one, partial quotients. I will probably revert to calling it repeated subtraction and hope you can see why that it's referred to that way as well. Okay, so we're going to have, I think it's a couple of examples. Is that true? Yep, 2 examples. One of them is going to look familiar, actually, to one we've seen today in your questions from last section. All right, I think you say this is Juan. I'm not really sure. We're going to go with Juan. Juan saved $5,340 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So this is a multi-step problem, and so we have to break down pieces of what we're trying to do. What's something that you see that we're going to have to do in solving this problem? 95 times 12. How come, Faith? Okay, the first year, or every month, he saved, so there's 12 months, he saved $95. This is going to help us to figure out how much he saved in year 1, right? So you can use whichever method you would like to use to solve this. I think I will use partial products. Why not? Let's go with it. So partial products is the one where we write this in a box. I have a box of 2 by 2 because they're both 2-digit numbers. So this is 95, and then I've got the number 12, so you can put the 10 and the 2 on the right side, or you can put it on the left side. Either way, it doesn't matter. And then you multiply each of the boxes together. So we have 90 times 10, that's 900. I have 5 times 10, or 50. 9 times 2 is 100. 90 times 2 is 180. And then 5 times 2 is 10. Did I get them all in there right? And then if we add them together, we have 900 plus 180, 50, and 10. So I have 1140. Did you get 1140? Yes. Okay. So that's how much he saved in year 1. That is not the answer to my question. What do I need to do next? Okay, so he had 5,340, and we're going to subtract the 11. Oh, it's 1140. That's very friendly. This is a very friendly subtraction problem because there's no regrouping necessary, right? You can just subtract each piece down. That's very nice. So we won't belabor any of our fancy techniques since there's no borrowing anyway. This would be 4200. 4,200. Okay, $4,200. What did we just find? What is $4,200? How much he saved in the last 2 years? Okay. What do we need to do next? How much you save per month? And there's a couple of ways to do that. What are your thoughts? So we could divide by 24. Does anybody have another thought? You could divide by 2 and then by 12 if you wanted to break it down into smaller values. And that might be helpful, especially because our multiplication facts that we know oftentimes go up to 12s these days. So it might be helpful to do it that way. You can certainly divide by 24 if you wish. I'm going to divide by 2, and then I'm going to divide by 12, okay? So we're going to do 4,200 divided by 2. It works really nice to divide this by 2 because it goes in so evenly, right? So beautiful, no complications for it. So there's a 2 and a 4, and then I bring my 2 down. 2 and a 2 is a 1. We do need to remember placeholders of zeros above the zero, so this is 2,100. And then I would need to do the 2,100 divided by 12. So let me do it with repeated subtraction, just so you can see it one more time, or partial quotients. So we would subtract 12 with as many trailing zeros as we can have. So I can't do anything bigger than a 2-digit here. So this would be 1,200. So this would be the number 100, right? I'm just going to write down the 100, like 100, the 10s, the things this time instead of times the 12s. So this is 100. So if I did 2,100 minus 1,200, what am I left with? 900. And you could have done this with the 24 as well. There's nothing wrong to have done it with 24. And then I can't do 1,200 again. I can do 120 though. Unfortunately, I'm going to have to do 120 quite a few times. So at least more than the last ones. So this would be 8. 8, that's a 7. 780. Look right? Okay, we do 120 again. 660. 120 again. 540. 120 again. 420. Having fun? 120 again. I have 300. 180. Oh, we're almost about to be done with the subtracting of the 120s. Zero got pulled away from its pair. Okay, one more 120, so that gives me 60. Okay, no more 120s. Now what? 12s. So I'll start a new column. So 60 minus 12. Again, no assuming that you know the multiplication facts by 12s at this point. So this is the number 1 that I've multiplied by. So then this would be 48, 12, 36, 12, 24, 12, almost done. One more time. I actually get a remainder of 0 this time. And the answer is going to be all of these values added together, 100 and something. How many 10s do I have? 70. So I have 170, and then how many 1s did I have? 5. So $175 per month, right? $175 per month. Okay. Dan. All right, we will set this one up. I won't solve the whole thing because it's almost identical to one we already did today. Dan has, not dimes, but he has pennies. 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as the third and twice as many in the second box as the first. How much money does he have in each box? So if I set these up with the same sort of mindset that I did on the earlier one, and I use variables, which box is going to have the first variable in it, the variable x, or whatever letter you want? The third box, because it says the first box has 3 times as many as the third. So the first box would be the 3x. What about in the middle? Yeah, it'd be that same 3x times 2, or 6x. And then combined, sorry, that should have started with 3. The 3x, the 6x, and the x would be the total number of pennies, which was 45.20, which is actually very nice on this one because it's just 10x. So if I'm dividing by 10 is so nice because you can mark out the 0, right? So division by 10 would give me 452 pennies. And then I can go back and I can figure out how many dollars that would be. How much is 452 pennies? Well, $4.52, right? And then I can multiply by 3 for the first box and multiply by 2 for the middle. I end up getting 13.56 and then 27. That's right, 27.12 in the middle. So I didn't show all the steps, but you'll forgive me for that, right? Cool. All right, I want to get to the last 3. They're all really quick. This is mental math and then computational estimation. And then we just won't do group work in class, and we'll just assign that as part of the homework, okay? So mental math, remember, means I'm finding the exact answer. I'm just doing it in my head, which means I can't just do any numbers of steps. 3 is our maximum that we're sort of thinking, 3 steps. So this one is called breaking up the dividend, and it works really nicely when we have pieces of what I'm dividing that are already divisible by my divisor. So in other words, the 63 and the 18 are actually multiples of 9, right? They're individually divisible by 9. So when I break this apart, I break it apart very much as 6,318 is what I'm thinking of it as. And I'm kind of writing it like this in my head, right? Because it's mental math, but you're going to write on paper. So if you did a 6,300 divided by 9, you'd get 700. And then 18 divided by 9 would be 2. For a total of 702. Okay, just like any time with mental math, it doesn't work all the time, right? The idea is that it sometimes works really nicely to think about something this way. There's another example that we have that breaks apart too, but it doesn't break apart as friendly as the last one. So the numbers 4 to 5 don't all evenly divide by 5. In particular, the number 4 doesn't divide by 5. And the number 42 doesn't either, right? I mean, it doesn't. But I still can break it apart and make it work really nicely by doing 425 like this, because 5 does divide 400. It doesn't divide the 4, but it divides 400 because it would divide 40, right? It would divide 40 and give me an 8. So this is 80, and then 25 divided by 5 would be 5 to give me 85. And then computational estimation. We've already seen compatible numbers in a variety of circumstances. Compatible numbers means changing this to being something that's going to be nicely and evenly divisible. What is a number that's really close to 4,132 that will easily divide by 4? 4,000 would be beautiful, right? Like, it's not going to give me an exact answer, hence the word estimation. But if I did 4,000 divided by 4, I would get 1,000. And that would be an approximation that's pretty good for what I'm working with. Okay? So kind of a front-end estimation, kind of a perspective.